Hello, this is the final exam review for the Physics Lab 204 final exam for Spring 21. You should have a study guide that looks like this. Please note that the exam is worth 50 points. Overall, the exam is not a huge part of your grade, that mostly it's the in-class activities that make up your grade, but it's not insubstantial either, so please be prepared. It consists of multiple choice and short answer questions or problems, and then there will also be one practical. You need to memorize the Lens equation, but you'll be given all other equations, and you should be able to answer all the multiple choice quiz questions, or all the multiple choice quiz and the free response too. So let's first go over the practicals. So first you need to be able to use the parallax method to trace reflected rays. So and you need to find the image. So if you recall, you put your mirror down and you drew a line on it, and then you drew rays. So let's say that this is your object right here. This is your object. You can put a pin right here and connect those two. That's your incident ray. And then you look over here and you put another pin so that this pin lines up with this pin and the image of the pin right here that is in the back of the mirror. That's called the parallax method. You should be able to draw that reflected ray. Also, you need to be able to measure the incident ray, theta I, and the reflected ray, theta R. Note that I can trace this back. The virtual ray is the reflected ray traced back, and then you should be able to draw another ray to determine where is the image. So this is my object, so I'm going to leave it right there. I'm going to take this pin and move it over here, and then I can draw another ray. This is my incident ray right here, and then using the parallax method, I can draw my reflected ray. Now if I trace this ray back, where these two rays cross, which is right here, that's where the image is. And that image you can calculate or measure with a ruler, Q, measure P, and of course P should be equal to negative Q. So that's the first, to locate the position of the image and measure the incident or reflected rays. The next practical is to be able to trace the refracted rays through a slab of glass. Remember, you take your slab of glass and you place it on the paper face down like this, and then you can take your pins and you place them like that. Now, you're going to take pins over here, looking through along the edge of this glass, like you'll crouch down sort of and peer through the edge of the glass, and you should find that your pins look something like that. That might be right, I'm not sure. I'm going to trace the ray. It will move towards the and then away from the, it moves towards the normal line and then away from the normal line. I was a little sloppy, but you get the idea. So you need to be able to measure also the appropriate angles to calculate the law, the index of refraction. That is, I need to calculate theta 1 and calculate theta 2. And I say n1 sine theta 1 equals n2 sine theta 2. N1 is for air, so that's what that is, sine theta 1, whatever theta 1 is, whatever you measure it to be, and then N2 is what you're solving for, times whatever theta 2, you measure these angles with your protractor, and then you can solve for the index or fraction of this slab of glass. We will be looking for your work to make sure that you have calculated this correctly, but of course you know that the index of the slab of glass is around 1.5. So if your number is far off from 1.5, then you might want to go back and remeasure your angles, because we might have some different materials, I don't know, but I think that all of them have an index that's about 1.5. If you get an index of 2 or more, or less than 1, then you made a mistake. So go back and retry that. The third practical, and you're only going to have one of these, is where you set up a single lens system here, and then you put your light bulb over here that has your screw on it, and then your screen over here, and you're looking for a place where you have a clear and sharp image. I like to look for the threads on this screw in the image. That's a good sign that you have a clear image. And then also be careful when you're measuring P, make sure that you're measuring the distance to where your object is, not to the center of the light bulb, but to where that object is. And then measure Q from the lens to the screen, and then you can calculate F, 1 over F equals 1 over P plus 1 over Q. You will not have a 2-lens system. Okay, you only have a 1-lens system. You only have one of those practicals. Now, for the Wheatstone bridge, you need to know what a Wheatstone bridge is. A Wheatstone bridge looks like this, where you have a known resistor, an unknown resistor, and then two other additional known resistors, RA and RB, and then this is connected at this point by a galvanometer. This is all part of a bigger circuit, like that. You need to know the purpose of a Wheatstone bridge. The purpose is to measure Rx, excuse me, to measure an unknown resistance, and it's a good tool for that. It was used for many years. We don't really use it now because we have digital multimeters, but back in the day, that's what you used. It was like a wooden box sometimes, and you put your resistors in, and you figure out what is the unknown resistance. So you understand the purpose of the Wheatstone bridge and what it means to be balanced. What it means to be balanced is that the potential difference between this point and this point is equal to 0. Those potential differences are equal to 0. That potential difference between those 2 points is equal to 0. When that happens, the current that goes through this part of the branch is equal to 0. So that's what you were doing when you had the slide wire. Remember, your slide wire made up RA and RB, and you moved your galvanometer wire on that slide wire until it was balanced. And when it was balanced, the potential difference between this point and this point was equal to 0. Balanced means that the potential difference between those 2 points is equal to 0, so that the current through the galvanometer was equal to 0. Okay, so that's what it means to be balanced. Be able to calculate the unknown resistance. We will be given this equation, Rx equals RB over RA. We gave it in terms too of the length. Let me just make sure I get this right. How we gave it. Yeah. We also said that this is equal to R times LB over LA, where LB and LA referred to the length of the wire. This would be LB and this would be LA on your slide wire. The length, how you split that slide wire into 2 pieces, and what is the length? So given these resistances for RB and RA, or the lengths LB and LA, be able to solve for what is the unknown resistance. Also, you need to understand, you see this in this equation, that R is equal to rho times L over A, and that came up in this lab quite a bit. R is rho L over A. Understand the relationships between R, rho, and the area. And know how to use that equation to calculate the resistance given the dimensions, the length, resistivity, and diameter of a wire. So understand those relationships. Let's look at tangent galvanometer. Tangent galvanometer, remember, was a coil of wire. It had a certain radius, and you use it to measure, we call this capital R, excuse me, used it to measure the magnetic field of the Earth. We found that the magnetic field of the Earth is equal to mu naught Ni over 2r tan of theta, and theta is your deflected angle. Okay, you had it set up so that the compass was in the direction of the magnetic field, and when you turned on the current in this coil of wire, it caused the compass to deflect, and that amount of deflection is our angle theta. This equation, you can go back to your lab manual and look at how we derived this, but it's based on the magnetic field of the Earth as well as what is the magnetic field generated by this coil of wire. So if I plot, as you did in class, if I plot Ni on my y-axis and, tan theta on my x-axis, Ni and tan theta, I find that since Ni is equal to 2RBE over mu naught times tan theta, that's right, isn't it? Yeah, so since Ni is equal to 2RBE mu naught over tan theta, that's just this equation, solve for Ni. This is my y variable, this is my x variable, so this represents my slope. So if I make this plot, doing all the stuff that you know about how to do plots, make sure that when you're finding the slope that you're not using data points, that you use a good best fit line, and that you're not using the data points, but you find the slope and set that slope equal to this expression, and then you can solve for the magnetic field. I don't know about the other faculty, but I'm almost certain I'll have a question like this because I want you to be able to do this type of graphing. This is really our last chance at getting you to graph and analyze data in this way. So make sure that you can be able to do this, especially in my class. I expect that's true for the other faculty too, but you might want to just double check. You need to describe the purpose of a double pole, double throw switch. Double pole, double throw switch is used to reverse the direction of the current. I'm not sure if your faculty are going to require you to do this, but I'm going to go ahead and describe it on page, on experiment 7 with the double pole double throw switch. It looks like this. I have a block. There are 6 terminals on the double pole double throw switch. If you look in the back of the double pole double throw switch, you see that there's a wire connecting this part, and there's a wire connecting these 2 terminals. So you have your circuit connected here. You have one part of your circuit connected here, and then another part of your circuit connected here. Now, you can have 2 situations in your double pole double throw switch. Let's say our current is coming here. You can have the switch in the up direction. In that case, the current flows through here, flows through here, and then back up to here, and then through here and there. Or you can have the double pole double throw switch in this direction, in which case the current flows through here. It travels across this wire, goes up through here, and then it goes through here. And it comes back up in the opposite direction, goes in this direction, goes up through there, and then goes in that direction. So you see, in this part of the circuit, by flipping it in the down or the up direction, I switch the direction of the current. There's a picture of this in that experiment for the tangent galvanometer for the double pole double throw switch. You should ask your faculty if you're expected to know how that switch works. Okay, so for reflection and refraction, you need to be able to locate the reflected rays and the image from a flat mirror. Went over that with the practical, but be able to do it too for the non-practical. Be able to calculate the index of refraction and refraction angles. Again, in the practical, you have to do that as well, but maybe also here, and I've already gone over that. You need to be able to sketch the array of light as it moves through a prism or a slab of glass. So I have a ray of light that comes in here. This is my theta 1. When it goes into this higher index of refraction, it's going to move towards the normal. And here it's going to move away from the normal. These 2 rays I hear will be, what's the word, collinear, I think, in the same line. They're shifted from one end to the other, but they're nonetheless in the same line. What I'm saying is that this angle, theta 1, is equal to this angle. So that's how you draw it through a slab of glass. For the prism, you have a prism that looks like this. I have a ray of light that comes in. It's going to bend towards the normal, like this. And then it's going to bend away from the normal like that. So that's how our prism works, bending towards and away the normal. I am not going to require you to measure the index of refraction as we did for the prism, where you had to find A and then you had to find the angle of deviation. I'm pretty sure that's true for the other faculty, but if you might want to inquire of them. Okay. Next, we have thin lenses. Be able to use the lens equation for a 1 or 2 lens system. So I've already done it for the 1 lens system. That is where if you have an object, your P is here, your image distance is here, that's your Q. And 1 over F equals 1 over P plus 1 over Q. So like for example, we might give you P and Q and you have to solve for F. Or I might give you F and P and ask you what Q is. And then in addition, you need to know how to find the magnification of that image. It's negative Q over P. We've done this in both 101 and 102 and 202, so I think we're okay on this. Know what the magnification means. A negative magnification means it's inverted. A positive magnification means it's upright. A magnification bigger than 1 means it's big. A magnification less than 1 means the image is smaller than the object. Also, you need to know how to do a 2 lens system. So on a 2 lens system, let's get rid of the second lens. I'm going to do two different ones. So first, say I put my object right here. This is P1. We have F1, and then you figure out where is your image for this. Say that this is Q1. All right, this is my object, this is my image, but that image becomes the object for the second lens. Now, let's first say, what if my second lens is right here? This is F2, and this is the way that you did it in lab, and it's probably the way that I'm going to do it in class for this question. This is your object distance P2, but please recognize that when the object is on the right-hand side of the lens, that this object distance is negative. This is called a virtual object. And it has a negative object distance. Then I can solve for Q2. I have 1 over F2 equals 1 over P2 plus 1 over Q2. But the big deal is here that this is a negative value. Whatever you find it to be, it needs to be negative because that object is now a virtual object because it's on the virtual side of the lens. Also, you need to be able to find the magnification. First, you find M1, negative Q1 over P1. M2 is negative Q2 over P2. Whoops. Negative Q2 over P2. And then the total magnification is M1 times M2. Now, you might have a more typical or traditional 2N system like you have in Physics 102, and that's where you have your lenses that are separated more distant from one another. I give you my object right here, so this is P1, and then you find what is Q1. Let's say that it's right here, so this would be Q1. And then you use this distance is going to be P2. Now that's going to be a positive object distance. This is a real object. And then you calculate what is Q2. It would be over here, for example. So this would be my final object, and then you can find out what is the total magnification, which is going to be M1 times M2. Okay, so that's a more traditional two-lens system where I'm not dealing with a virtual object, but I'm dealing with a real object. Also be able to describe, draw a diagram, and calculate the spherical aberration of a lens. So in a lens, what I have is that light rays that come on the outer part of the lens will focus here. Light rays, on the other hand, that come to the inner part of the lens will focus here. So that is called spherical aberration, that difference in the focal length of this lens. The difference in the focal lengths is equal to the value of the spherical aberration. How much spherical aberration does this thing experience is that difference in focal length. So that's how you calculate it, is you just take the difference in the focal lengths, measuring on the inside of the lens and the outside of the lens. Yeah, that's all. And then spectroscopy, you need to identify an emission spectrum as either hydrogen or helium. Look, really easy, because hydrogen is a pretty simple atom, just a proton, an electron, that it has a very simple spectrum. So this is hydrogen. And if we give you the data, then you'll just have, 2, 3, maybe 4 lines in that hydrogen spectrum. The helium spectrum, on the other hand, is much more complicated. So there's two protons, 2 electrons. So you just have a lot more business going on with the helium spectrum, and so it's much more complicated. Be able to describe the physical properties of stars related to their spectral type. I don't know what your faculty are going to require of this. There is a section in your lab that talks about the emission spectrum of stars, and that stars, show their different, the hydrogen and helium emission spectrums in their atmosphere. So and then it also talks about how you have these other absorption spectra. So look back at your lab manual in experiment 11 on that topic. And then finally, the diffraction grating. So with a diffraction grating, I'm going to use a double slit diffraction because it's just a little simpler to see, but this applies to a diffraction grating too. In a double slit, you have a diffraction pattern that looks like this, where this is a bright spot, so the little hump here on top on this diagram, it measures the intensity and it denotes a bright spot. Look, I'll do it in yellow. So that's a bright spot, this is a bright spot, this is a bright spot, here as well, and here as well. And then there are dark spots in between here. So you have this series of bright and dark spots. I can measure the angle from the optical axis. Say the angle up to this second bright spot is this angle right here. This is a second order bright spot. See, m equals 0, m equal 1, m equal 2. And then the path length difference, there is a path length difference of the two rays that travel from here to meet at that point. And the path difference is equal to d sine theta. In order to get that constructive interference in the second order, this has to be equal to m lambda, where m is equal to 2. D is the separation between the slits right here, and theta is this angle. So you need to be able to describe that relationship between the wavelength diffraction angle and the slit separation. Now this is for a double slit, but a diffraction grating is really similar to the double slit. In fact, the diffraction grating follows that same equation, d sine theta equals m lambda for its diffraction pattern. So it's an identical diffraction pattern. That is how the bright and dark spots are presented on the screen. But the diffraction grating itself looks a little bit different. So whereas with the double slit, you just have two slits like that. With the diffraction grating, you have many, many, many slits. So you might have thousands of slits in a diffraction grating. And so when we talk about diffraction gratings, we don't usually give the separation between the slits. That's going to be tiny, right? This was a centimeters, biggish, but on a diffraction grating, the separation between the slits is really tiny. So like, for example, we might say that the slit spacing, I think in your lab, you had a slit spacing of 1,000 lines per millimeter. So if you want to figure out what D is, you need to take the inverse of this. 1,000 lines per millimeter, or that's equal to 0.0 tens hundreds 0.01 millimeters. Now, if you want to think about this, you can say millimeters per line. You don't need to do the per line, but it just means that there is 0.001 millimeters between those two slits. So you would convert that, of course, to meters, and then that would be equal to your slit spacing for diffraction grating. We're doing that in class too, so be able to describe the diffraction grating and that relationship. I think that's all. So good luck. Don't stress too much over the final, but don't just completely disregard it either. It is important. It's just not the most important thing in your lab grade.